Hello everyone, good morning. In this presentation, I'm going to introduce you to our project, which is a super efficient low carbon air conditioning system under the category of environment and energy with subject title of carbon footprint reduction. Our team name is MARKONI. Before we start, let me introduce you to our team. We have our advisor, Associate Professor Divram Aiden, then me and Bara Adam as the team leader. Also we have Badruddin Mustafa, researcher, Abdurrahman Hassan, who will be documentation specialist, Amin Faisal, also a researcher, and Gabbani Ammar, an analyst. In this presentation is going to be me and Gabbani Ammar. Let's start by the summary. Our system is going to be one of its kind. It will be an affordable multi-pass regenerative evaporative cooler. It will be also suitable for hot climate. It uses water instead of refrigerant. Our main motivation is to develop a high efficient alternative to the vapor compression system. To do that, we're going to follow the following methodology. We will design the system in SolidWorks, then we will run simulation in a CFD simulation to analyze the key parameters such as air temperature, air humidity, and velocity. And then after that, we will manufacture the system and test it to validate our results. The innovative part of the system, it's going to have a high COP coefficient of performance up to 10, or may also increase more than 10, with bulb effectiveness of 100%. Also, we are going to implement a smartphone application to control it remotely. The problem statement: our system is going to follow the Sustainable Development Goals. As you know, over 1 billion people lack access to cooling, especially in poor areas. 12,000 heatwave deaths per year projected to rise by 2050, and also 4 billion people may lack AC by 2050. And the conventional HVAC systems contribute to a high percentage of grid electricity, and part of it is the vapor compression, which contribute to 7% of the global electricity consumption and 3% of the greenhouse gases emissions. Therefore, an affordable, accessible, sustainable cooling solutions are urgently needed. As you know, there are multiple types of evaporative coolers, such as the direct evaporative, indirect evaporative, and dew points. All of them has their weaknesses, and we are aiming to overcome these weaknesses to make a system that have all the positive points. You can see in the table, our system is able to have 16 degrees Celsius temperature difference with cooling capacity 2050 watt and wet bulb effectiveness of 1.26 and dew point effectiveness of 0.84. You can see in this slide multiple types of evaporative coolers. The table is the global warming potential of some selected refrigerants. You can see that the refrigerant used in vapor compressor ACs have a high global warming potential compared to carbon dioxide, up to 2345. You can see in this slide our system is using the air configuration in the top right figure. Here we have two air streams. The green one is the dry stream and the blue one is the wet stream. First, the dry stream enters the heat exchangers, then it multi-passes the heat exchangers until it exits. When it exits, it gets cool, and part of this air will be reintroduced to the system. This part is going to be the regenerative part of the system. After that, the 4- is going to work as the wet air stream. It will be humidified, some water will be spread on it, and this part will act as direct evaporative cooling, and then it will get cooled to transfer the cooling energy to the dry part of the system. But as you can see or notice, this in this dry stream, no water will be introduced. It will stay dry from the beginning until it exits the system. The 4 here is going to be the product, and the 7 is going to be the exhaust, and here number 1 is going to be the inlet at the back of the system. We did some preliminary testings and we got the results in this graph. We had an inlet temperature of 35 degrees with an inlet relative humidity of 33. At the outlet, we got air temperature of 20 to 19, almost 19, with relative humidity around 67. Therefore, our system has a high potential, can produce really promising results. For the methodology, we will start by doing conceptual design and literature review, and we're going to see what are the sustainable cooling challenges in Turkey, and after that we will optimize our our system using SolidWorks and design it using SolidWorks. After that, we will do some computational analysis and simulations in computer softwares. Then we manufacture the prototype and select the materials available in Turkey. After we manufacture the system, we are going to carry out some experimental testing under laboratory conditions to validate our experimental results. Next, in the commercialized potential and sustainability, I will let my teammate Gabbani to talk about.
Hello everyone, I'm going to be taking on from here, starting with commercialization potential and sustainability. Now, to explain and assess commercialization potential, we need to first see the savings that we get from our supercooled unit. To be able to get a standard sample of savings, of annual savings, we first assume that we replace 100 vapor compression AC with supercooled units, and we assume that both of them are operating at a load of 4 kilowatts. Accounting for each of their coefficient of performances, dividing 4 kilowatt by the coefficient of performance of supercooled and 4 kilowatt by the coefficient of performance for the vapor compression, we can find how much each unit consumes electric power. From there, we can multiply by 120 cooling days and the number of operation hours in a day, which is 10 hours, and subtracting the two values will give us the savings. So now we have 1.2 megawatts of electric power saved, 1.4 gigawatt hours electric energy, 8.6 million tele, and 420 tons of CO2 emissions. Another unique selling point for our supercool is the use of water as a refrigerant, which means low capital cost and also less energy consumption, as well as we eliminate the global warming potential of the refrigerants used in the market. For the market potential, we can see that the market in Turkey almost doubled from 2.2 billion to 4.5 billion in 6 years starting from 2023. For the global market, for the evaporative coolers, it has also doubled from 9.3 to 19 billion. Now, furthermore, to explain the potential of commercialization of our device, of course, it will have added value on the low-cost, sustainable air conditioning. This will support Turkey's technology initiative as well as Turkey's commitment to sustainability. To ensure the long-term continuity of the project, we can obtain funding from TÜBİTAK as well as we can seek industry partners. Therefore, we can say that our project is open for new projects and business collaborations with existing heat exchanger manufacturers from Turkey as well as water pumps and fans. Our device Supercool is comprised of aluminium plate heat exchangers, acrylic cover known as plexiglass, an axial fan, water pump, and evaporative cooling pad. All of these are manufactured by Turkish companies based in Turkey. Due to our device high performance, low operating cost, and portability, we can surpass the vapor compression air conditioners. In terms of evaporative coolers, only direct evaporative cooler is manufactured in Turkey, which is not suitable for indoors due to moisture added to the product air. Our supercool unit, its capital cost is medium, very high performance, and of course very low environmental impact and very low operating cost, and of course suitable for indoors. Our target audience is the Midland and Eastern regions in Turkey. As you can see here, each number shows the relative humidity in the region, and as the color gets more red, it shows a low humidity, and as the number goes more towards green, it shows a high rate of humidity. And as you can see on the map, most of the regions are more red colored than green, which shows that the environment and conditions is very suitable to our device. Domestic buildings, apartment buildings, and commercial buildings all in Turkey need this supercool device. As for the project timeline, we first started with work package 1, which is the design of the system, which includes the air path design and the frame design based on the selected airflow design, and then the mathematical modeling and simulation, which includes thermal analysis and mathematical modeling and the simulation for the system. Work package 3, which was manufacturing and integration of remote system controls. Actually, we went ahead of our timeline and finished the manufacturing system components, and even, as my colleague mentioned before, we started preliminary testing. Last is the experimental testing and optimization. For the SWOT analysis, you can start by mentioning that our device has an affordable capital cost, also an up to 75% power savings. Also, the device is eco-friendly as it uses water as a refrigerant. If you can say weaknesses, our device has a high performance in low humidity, but this can be impacted at extremely high humidity levels. Also, it requires that the air exhaust are exhausted out of the room. Also, maybe not a lot of people are aware about the importance of evaporative coolers. For the opportunity, there is a huge green cooling technology demand that is not being met, so there is a huge market opportunity for us here. As for the threats, it needs some water management, but that's not to be feared because the water returns back to the ecosystem, and also harsh conditions may affect the high performance of our system. Finally, I should be saying thank you, and we should be cooling the future sustainably. Thank you.